Good evening, all of you. We'll start our session in 1 or 2 minutes. So, all right. Good evening. I'm Vijay Rahane, and today we are here to discuss some of the problems based on the course study guide in the organic retrosynthesis, a problem-solving approach. And we are up to, we have almost finished the 4 or 5 weeks of this course. And already we have some background of the most of the concepts which we see in the retrosynthesis, particularly the introduction and basically we have used how this retrosynthesis is useful in our day-to-day life of the organic chemist or synthetic chemist, and some terminologies which are generally used in the retrosynthesis like retrosynthetic disconnections or the transformations and some terminology or similar terminology that we have already discussed, and with the help of some examples. Now we are slowly moving to some advanced problems in the field of this retrosynthesis. And in the last video or the last session, we have already discussed this chemoselectivity, radioselectivity, as well as the we haven't covered yet the stereoselectivity, which we will see uh, on the next week. But today we are here up to we already covered the chemoselectivity and radioselectivity and also see some of the examples. So before moving to the session, so I would like to take a call from you. If you guys have any doubts or the questions regarding the topic, so that we can discuss here today. Sorry, right now, or you can stop me in between. In between also it will be okay. We can discuss that one. So if anyone have any doubt, you can put your doubt in the chat box, or also you can unmute yourself and uh, ask a question in between. And also, I like to mention I have added the link for the OneDrive, so you can access my these slides through that OneDrive link, Google Drive link, and you can download these slides which I covered in the last videos as well as the this video. Okay, so we'll move to the some of the questions. If you don't have any doubt, I will discuss some of the problems in this regarding these topics. So the first question here is the so this is the your target molecule, and how one can achieve the synthesis of this target molecule. So if we do the disconnection or the functional group inversion, so on functional group inversion, this can be achieved. This target molecule can be achieved from this intermediate, and this intermediate further can achieve from such type of uh, starting metals, this and this phenyl magnesium bromide. So if you look at how one can synthesize this, so let's start the linear synthesis of uh, this molecule. So let's say we have this type of what we call reagent, and we do the reaction with this PHMGBr, which is a Grignard reagent. So what it will give on the linear synthesis, so this is a ketone, and ketone on reaction with the Grignard reagent, it gives the this OH, and here that it will be a pH. So if you do the tosylation of this hydroxy group, what it will gives on reaction with the tosyl chloride, so it will give the OPS. So this pH will be remain as it is, and on this six member ring will be remain. And further on addition of the base, so here there are the protons, so it can gives the E2 elimination, right? So on E2 elimination, so this OTS group can eliminate and we get this type of intermediate, and which further can be leads to the on reduction of this double bond, we can get this pH, which is our target molecule. So I will just crop other part, just remove other unnecessary part. Okay, right. So in this way, you can achieve the synthesis of this molecule. So this was our first question. So I hope you don't have any doubt in this question. So here I have just shown, just to save some time, I have directly shown the synthesis. So this was our starting material one, and this is our starting material or the reagent. And upon this reagent, this is the Grignard reaction, right? So I'll just write down the shortcut, the Grignard reagent, addition of this Grignard on the ketone. So what it will give, the alcohol, and on we just convert this alcohol into good living group, because directly this alcohol is not that good living group. So we just convert that into the good living group, and then we did the elimination reaction. So upon elimination, what happened? We get this double bond here, and so in our target molecule there is no double bond. So we have converted this intermediate to the our product by doing the reduction reaction. And how we can do this reduction? By adding like the palladium catalyst and the H2 palladium or platinum catalyst. So it's just a simple reduction reaction. Right. So I hope uh, you got the answer for this now. Now we'll move to the next question of this similar type next question. So this is the second question. I'll just remove the other part. All right. So we have this is the our target molecule, and how we can achieve the synthesis of this target molecule. So you can see here. So this is basically here we can do the disconnection, and upon doing disconnection here, this can be the ketone, and the other another part is here. So if you look at here, this is negatively charged now. So is it possible to get negative charge on that carbon atom, which is a carbonyl carbon? Yes, it is possible. How it is possible? By doing the amplong. That is, this can be, this is the pH, and this here it is the hydrogen. Have you heard the concepts of amplong? So we can reverse the charge polarity by making it into the uh, structural modification. So in this case, you can see, so this is the basically this can be achieved from the this H C double O pH. So we just convert this into the this type of material by just adding the alcohol 1,3 diol, right? And this obviously we need the acyl catalyst. So basically, this is kind of we have converted this compound into such a compound, and now this proton we can abstract this proton. So upon abstraction of this proton, it can be now this O this center gets negatively charged now with this phenyl substituent, and we can add this one to this starting material that we have. So this negatively charged, now we can attack this negative charge on this carbonyl center to get our this starting material, sorry, this target molecule. So which is like this. This this can become now the hydroxide, and this is the this is now Volado. Initially it will be like this, and here it will be pH. So from the center, okay, so this is the pH, and like this. And upon deprotection of this entire reagent, entire, sorry, the side group. So this side group, we can do deprotection of this group. So it gives our target molecule, which is this one, pH, OH, and now it has now the pH like this. So basically, this is in this way we can do the retrosynthesis of this one. We already did the retrosynthesis as well as the forward synthesis in this case. So up to here it was the retrosynthesis. So yeah, yeah. So from here, so like this, we can do the retrosynthesis. The first, this is just basically we did a disconnection, and this is the synthetic equivalent of these species. Which species? I will just rewrite this species just for clarity. So this is the synthetic equivalent of, if you look closely, this is negatively charged carbonyl. It means we can achieve this negative charge on the center from such type of species pH. And how we can synthesize this? So for that I have shown here. So this is way, in this way we can do the synthesis. This is basically the benzaldehyde plus this diol and followed by the proton attraction from this position. So we'll write down here a proton. So this is the synthetic equivalent for this species. I hope this example is clear now. Now I will take the another example, which is this one. So this is another example, and in this example, so this is also one approach how we can actually do the retrosynthesis of this molecule. This is the same molecule as earlier we have seen. Right. So in this case, what we can do? We can do the disconnection here as well. So what we get? We get this double bond O here negatively charged, and this pH also the OH. This is now positive, and along with this double bond O pH, right? And how we can achieve this from? This is obviously the synthetic equivalent of pH double bond O double bond O pH, right? So this is what, and also this you can do the retrosynthesis of this as well. So how it will be? So as you can see here, this is the functional group interconversion. So this can be achieved from this beta hydroxy ketone, and this beta hydroxy ketone. If you look at how we can achieve the beta hydroxy ketone, so you may have heard like one of the name reaction, and this from the aldehyde benzaldehyde, this pH double bond O H. So two aldehyde we can condense together. So what is the name of that name reaction? So I will just give you homework. Name reaction. So this is one of the name reaction in which we can convert benzaldehyde into the such type of beta hydroxy ketone.
It's benzoin condensation.
Yes, this is the benzoin condensation reaction. So we can do the two molecule of aldehyde, we can condense together and it forms the beta hydroxy ketone. So in this way, we can do the retrosynthesis of this molecule, and the forward synthesis, I think it is easy to do now. So we can do the first step. I will just show here how one can achieve the forward synthesis. So this is just first step, the benzoin condensation. The second step is just the oxidation, benzoin condensation. This is just oxidation, and the we can achieve this one. Now the question is how we can achieve from these two molecules, how we can achieve this one. So if you just do the at the base, it forms the enolate anion here, and which can attack here. So it gives our target molecule. So in this way, you can achieve the linear synthesis for this molecule as well. So these are some three examples that we have seen, which is based on the similar category. Uh, the second and the third, these are just two different synthetic group for one molecule. So now we'll move to the some disconnection approaches that can be achieved by using the Diels-Alder reactions. So this is like a cyclic framework. We generally, most of the target molecules generally have such a cyclic framework. So how one can achieve the synthesis of this, or how we can do the retrosynthetic analysis for such cyclic frameworks. So I will not show this in much more detail. Basic concept here is the Diels-Alder reaction, and that you should know. So what Diels-Alder reaction? So just do the reverse of this so you can understand what is Diels-Alder reaction. So this is 4 plus 2 cycloaddition reaction. So this is the double bond. So this is the olefin, and this is the diene. So this is, it has the 4 pi electron, it has the 2 pi electrons, and in place of heat, they gives the formation of such cyclic product. Now here forget about the stereochemistry, whether it is endo or exo, it doesn't matter at this stage now. So this uh, diene and the dienophile, so under the heating condition, it gives the formation of cycloaddition products. So this is what we get from in this step. So we just arrow. It's the direction of the arrow is like this. So these are the starting material, and this is the product, right? So and similarly, how one can use such Diels-Alder reaction in the retrosynthesis of such molecules. So in this on the left hand side, these are our the target molecules, and if you clearly observe all these target molecules, all these molecules involve the one step, which is Diels-Alder reaction. So that we'll look here. Let's test. Let's take the first example. How we can achieve this synthesis. This is the target molecule. I'll just give the A and the B. This is the. I'll just erase this Diels-Alder reaction. Okay. So this is our target molecule one. And if you look at here, we can do the disconnection here. And what? what was the how one can achieve this one reverse or the linearly. So this is basically a Wittig reaction. Upon Wittig reaction, this ketone can convert into the such olefin. So that's you need to uh, keep in mind. So this is Wittig reaction. Here we can do the disconnection. So this is our the uh, first disconnection. Then the second step, how one can achieve. This is basically this is diol-Sandler reaction here. So this is the dinophile and this is the dine. So these are the two starting material one and the starting material two. So from these two starting material, one can achieve this intermediate one, and from this intermediate one, we can achieve this target molecule one. Similarly, if you look at the second example, in the second example, sorry, in the second example, we can see here. So how we can get this molecule? So if you look closely on this molecule, so this is basically this 2-methyl group we can attach on the from the ester. So this is basically this entire 2-methyl and hydroxy. So this is basically the we can achieve from the ester. So on ester, if you do the Grignard addition and if you add the more than 2 equivalent of the Grignard reagent or more, so what will happen? So the first signal attached on this ester, it will give the ketone. So the first addition gives the ketone, and again second addition gives the this alcohol. So right now we are in position to understand how the Grignard reaction works. So I will not show in detail, but this is basically the Grignard reagent addition and two equivalent. So this is basically the first step was functional group interconversion. So alcohol can be achieved from this type of, or we can also call it as a disconnection as well. So this alcohol target molecule can be achieved from this ester, and how this ester can be achieved. So this is basically that we have already seen. This is from the this type of uh, double bonded compound. You just here you just functional group interconversion. This is the uh, this part is the olefin, and here it is alkane. This is alkene, so this is FGI, functional group interconversion. So this can be achieved by this way from the starting material. Now, when we move to the another starting material, okay, sorry. So this can be achieved from this starting material. Now, how the starting material can be achieved further? We can achieve this. We can break down this molecule further by disconnection and from the Diels-Alder reactions. So these are the starting materials, and these are the starting materials for the Diels-Alder reaction. So if you just look at the linear synthesis from this molecule, I'll just remove unwanted part. So if you just go step by step uh, to understand linear synthesis, the first step was the Diels-Alder reaction. The second step, we can do the reduction of the double bond. And the third step, we can just do the simple Grignard reagent addition. Diels-Alder, this is the reduction reaction by using the H2 palladium or the platinum, Diels-Alder just by heating. Then here the Grignard reagent, right? And more importantly, more than two equivalent, because this ketone can now convert it. We want it into the alcohol, so we need to add more uh, equivalent of the Grignard reagent. more than 2 equivalent. All right. So if you look at the another example given here, which is again much much more similar to the previous two examples. So what is there in this example? So here the starting is the ketone, and further this ketone is similarly achieved can achieve from such type of uh, ketone with contain double bond, and this can further break down to the similar dials order starting materials. So I don't think you really need to discuss this question at least. So just refer the earlier one. So we'll move to the next question. Next, some approaches. All right. So here some different type of retrosynthesis given, and so in this example, I will directly show the answer. Sorry, the solution for this one. So if you look at this is our target molecule. We can uh, see this is a too complicated starting material. But if you just break down this into the simpler one, so this is the first disconnections we can do. So this is one starting material. This is another second starting material. Further, this ketone can further achieve from this alcohol. We're gonna see the linear synthesis. From the linear synthesis, we will understand this example much better. But yes, from this ketone can achieve from this alcohol, and further this alcohol is obviously from the CH2PH MgBr, that is the Grignard reagent, negative, and this is the this C double bond O ET. So this two equivalent of this CH2 negative. So if you just look at now the linear synthesis, two equivalent of this PH CH2 negative, this can attack on this position twice. What it gives, in the first step it will give the ketone, and on the second attack it gives the alcohol. So this is alcohol we get upon the two times Grignard addition of this PHCH2 MgBr. This is the Grignard reagent. Of addition of this Grignard reagent on this ester, it gives this alcohol. And now alcohol we know how to oxidize this alcohol. So just simple oxidation. You can use any oxidizing reagent. It will give simply this ketone. Now the question is how these two molecule gives the formation of this target molecule. So what are the reagent conditions required to achieve? So I will show the next slide just to focus on the same the up to here we have understand how to get this molecule. So I will we don't require this remaining part, right? So I will just remove that part. Now the question is how these two starting materials, so this is one and this is two, react to form this target molecule. So what will be the reaction reagent condition? So if you look closely at this these starting materials, what we can observe or what we can notice in these starting materials. So it has the two alpha hydrogens addition to the ketone, and the second starting material has the what it has the carbonyl group, that is the center for electrophilic centers. So if you add the base, So these protons are easy to abstract by the base. Once this proton is abstracted, the negative charge form here on this carbon. So I will just show this one only. So the negatively charged form on the alpha carbon of this keto can attack here. It gives this O negative and finally OH. The second from the another side also this can happen, and basically it will give this some sort of intermediate. So pH, it has the OH here, also has the OH, and this is the newly formed bonds. And this starting, I will write down with the green color, the starting compound 2 pH. Still, it has the one proton here and another proton here. Right. So this sort of intermediate we can get. So this is just theoretically that I'm saying. I'm not sure which intermediate, what sort of reaction mechanism is getting followed. But overall, we can say like this intermediate it can form, and potentially since our reaction already has the base, so the another protons can also be easy to abstract by that base, followed by such type of elimination reactions occur from the both sides. And what it gives, it can give potentially uh, this type of has the pH here, pH substituent here, and the pH substituent from this side, pH. So like this target molecule, it can gives. So basically the reaction needs the base. In place of base, we can get the type of starting material. All right. So any doubt up to here? We can move to the next question. If you don't have any doubt, or let me know if you have any doubt. Excuse me. Okay. So this is now one of the uh, real life example for retrosynthesis that I have taken. So if you look closely at the example, so this is basically chlorobenzide. So this chlorobenzide is used to kill the mites and the ticks. So this uh, we can use this is a commercial pesticide used to kill the mites. And if you look at the retrosynthesis for this molecule, how one can synthesize this molecule. So very simple. So in this case, it is just a sorry, one disconnection. So we can get this simpler starting materials. And if you look at the this is the synthon, that is charge species. How the synthetic equivalent for this one? The synthetic equivalent can be either CH2X, and this X can be either chloro or bromo or iodo compound, or maybe tosylate, basically a good leaving group. And if you look at the linear synthesis, so this is the starting material, this is the starting material A, and this is the starting material B. So this is A and B. If you look at the linear synthesis, so what in presence of the base abstract this acyclic proton. So if you look at in the both the starting material, which proton is most acidic? So here this SH proton is the more acidic, so it forms the S negative, and once this S negative form, it attacks on this carbon which has the chloro group, and this chloro can be displaced by this sulfur. So this entire S sulfur containing side group can attach on this center, this carbon center, right? And we get the formation of our chlorobenzide molecule. So you can note down this one. The next question is, sorry, next retrosynthesis is the cation ethyl ester synthesis. And this is the one of the API used to lower the blood lipid level. And so this cation ethyl ester has the this R is equal to C15H13. That's basically the alkyl chain like this, just right. So we just label it as a R for now because we are not gonna worry much about this R group. And if you look at here, how one can achieve this synthesis. So the first step was the disconnection, and we can use this disconnection here from the this RBR. So we need to have such long bromide. So how much it will be? It will be C15. So this is C15H31 Br. So this is what basically the starting, right? So you just write down the general formula. So this is the alkyl bromide, and another remaining part is this is the ester, and I believe this is the commercially available ester. Otherwise, we can also do the further retrosynthesis of this uh, ester, amine ester also, but it can be doable. It is just this is the ester part and this is the amine part. So basically, this ester part we can get from either from the acid or this entire part we can get from the some other substrate. But anyway, we limit our retrosynthesis up to here only. So this commercially available amino ester, we can do the esterification. Sorry, this is the acid. We can do the convert into the ester, and this ester further on reaction with the this alkyl bromide, it gives this formation of this ketabine ethyl ester. So that's our target molecule. So just a two-step synthesis gives this uh, commercial drug candidate. Now another, this example I believe we have already covered once a while. Once I think in the second week or the first week videos. Anyway, we'll discuss this here also quickly. So this is the one of the starting material. Sorry, the target molecule, which is the ICH D714. This is the potential anti-obesity drug, and how one can achieve this retrosynthesis for this molecule, or how we can do the synthesis for this molecule. Basically, if you look at here, it has the A, B, C, D, four different type of disconnections possible. So either we can do the disconnect here. So this part can be achieved from this part plus this part. We can also do the disconnection at this point. So what we can get? We can get this part plus this part. Further, we can do the disconnection here. So we can get the pH CH2NH2 plus this another part, or also we can do the disconnection here. So we get the entire amine plus this pH CH2Br part. So there are various possible disconnections possible for this molecule. You can just note down how we did the disconnection in this molecule. So, and they are the logical disconnection. They are not any random disconnection, because if you look at here, whatever the product forming, whatever the synthons forming after the disconnections, they should have the synthetic equivalent. So let's see one by one. Let us say, so on this disconnection, the first one, so this entire alcohol, so the O negative, it can be achieved from this alcohol, right? So this entire part, so this entire part, so this entire part O negative, and which has the synthetic equivalent, obviously the this phenol OH, right? Similarly, the another part, this is the pH CH2. The another part is the pH CH2 positive. This part was O negative. Now this should be the positive, right? And this can be achieved from the this bromo CH2 pH, this BrCH2 pH. So now if we look at the bond polarity, so this negative and this is positive. So the first disconnection logically correct. If you look at here also, this is again pH CH2, this is positive, and this part negative. So upon doing disconnection here, this is also logically correct disconnection. If you look at this disconnection, where it has did up at this point, this pH CH2 NH2. So this part, so pH CH2 NH2, this part is there, and now this remaining part is the bromo derivative. So basically, upon disconnection here, so this bromo can be uh, one starting material. And the fourth disconnection, that is this one, how it has did at this position. So upon doing disconnection here, if you look closely, so this is two part, this O negative and this CH2 positive. This O negative we have already seen. This can be achieved from this phenol derivative, phenol. Now the question is this NCH2 CH2 positive. That's basically this one. And what will be the synthetic equivalent for this derivative now? I will drop all remaining part and only focus on this part. Now, if you look at this synthon, this can be achieved from pH CH2 N CH2 CH2 like this, either from this one or pH N, not cyclic. Just from the linear also we can achieve pH CH2 CH2. Uh, this can be either iodine or bromine. So that basically good living group. So from this one, these two possible synthetic equivalent for this species. So they all disconnections are logically correct. Okay, now we'll take the next retrosynthesis. This is basically a retrosynthesis for the, this is the one of the apoid painkiller, and the structure is like this. So you can have a look at the structure. Now, if you want to do the disconnection, the first disconnection here is at this bond. So basically, this can be the NH, sorry, N negative, and this can be from the this amine. The another part, this one can be chloro substrate, and this can be achieved from the acid CH2 AME, right? So it has the further electrosynthesized starting material stable, because the acyl chlorides are generally not so stable. So we can do the synthesis of this acyl chloride from these acids as well. Now this intermediate can further break down to imines. So like this imines, and further on this imines, we can do the disconnection here from the ketone and the amine. So this is basically CN sorry, the imine formation. So if you just look at the linear synthesis for this molecule, so if you look at the linear synthesis, what it was, so these are the two starting materials. So this amine plus ketone, what it gives this imine. So in case of just H plus acidic condition, it forms the imine. Now this imine we can do reduction of this imine to get this target molecule. So what we can add for reduction of this imine? NaBH3Cn, sodium cyanoborohydride. So upon addition of sodium cyanoborohydride, we can do the reduction of the imines to amines, right? And once we get this amine, we can do the reaction of this amine with this acyl chloride. It gives the formation of this fentanyl compound, whatever it is, but this is our target molecule. We can achieve the synthesis of this target molecule. So this was the linear synthesis. Any doubt up to here? Okay, this is the next example, very similar. And I believe I should not, there is no need to discuss this one, but I will just show very quickly. So this is the fenfluramine. This is the neuroactive drug. So ignore about the whatever name given for these molecules, but you just focus on the retrosynthesis for this topic at least. So this is our target molecule, right? Now, if you want to do the retrosynthesis of this molecule, how we can achieve the synthesis of this molecule? So basically, here this target molecule can be synthesized from this molecule which has this. Here there is a ketone, sorry, the carbonyl group, and further this carbonyl we can do the disconnection at this point, so it can be achieved from this amine, and further this amine can be from this ketone, and this is as they have given to here, most likely this is the starting commercially available. So we have given did the retrosynthesis till simplest possible starting material. How one can do the synthesis of this molecule? So the first step was the imine formation. So we know the simple reaction. So the ketone plus NH2, what it forms? It forms the imine. So this is basically just imine formation reaction. Then the second step is reduction of this imine to amine. So this is H2 palladium catalyst. So this imine is converted into the amine NH2. Now, when you did this reaction of this amine with the acetyl chloride or acetic anhydride, so what it will happen? So on reaction with the acetyl chloride, so this is basically this is the one. So this can gives the first step CF3 NH, and further upon reduction of these amides with the LiLH4, what will gives? It gives the amine. So for that we need to know how the uh, reduction works. and what is suitable reagent. So that we have already covered, I think, in the first or second video, right? So the first step was just simple imine formation from this ketone. So it formed this imine, then reduction of this imine to amine. So it gives the NH2. Then step is the acetylation of this amine. So this just basically the acetyl protection of this nitrogen, and then LiLH4. So now it forms the amide. So this is functional group is amide functional group. Now if you want to reduce this total amide functional group, what we can do? Forget, here there was a methyl. So if you want to do the reduction of this amide, what one can do? We can do the reduction of this amide. It gives the amine. So that's our target molecule, right? So I will just quickly show the reduction reaction because I believe here you need to understand different reduction reactions as well. Okay, this is the last slide that I have taken from the second week video, and the mic was muted actually. I purposefully kept the mute. So okay, so anyway, so I hope I'm audible now. So this is the last slide. This is the slide. Sorry, not last slide. This is the slide I have taken from the last week video. So in which we have seen how the different reducing reagent works. So in which we can see this LiLH4 directly reduce this imine, and obviously how it will be, it will directly use this NH2 that I haven't mentioned here. But yeah, so this amide LiLH4 is quite strong reducing agent, and this can reduce this uh, amide to amine. So there should be one carbon, CH2, CH2, NH. Sorry, here RR. So I just write the R, R double dash, R dash, R double dash. So like this. So you know to know when you are studying this retrosynthesis course, so you should know about at least some basic reactions, and this is one of the important reactions reduction. I will just quickly revise these concepts of this reduction. So if you have the H2 palladium catalyst, it can reduce this imine to amine, aldehyde to alcohol. Second, if you use this Na sodium cyanoborohydride, NaCnBH3, that is we often see NaBH3Cn. So sometimes we just got confused just by different representation of this same reagent. So don't get confused. So here it can reduce this imine, and at some point some reactive acids, sorry, aldehydes as well. But doesn't and imines can convert into the amine. Obviously, aldehyde can convert into alcohol. If you have the NaBH4, so it reduces the imine to amine, alcohol, sorry, aldehyde to alcohol, and ketone to also the alcohol. So obviously, this will be primary alcohol and this will be secondary alcohol. So that's just you need to use some common sense as well. So another LiBl, Li BH4. So this reduce this imine, aldehyde, ketone, and also esters. Then another reducing reagent is the LiAlH4, and this reduce all this imine, aldehyde, ketone, esters, amides, and some reactive acids as well. So the reaction is not much efficient reduction of the acid by using the LiLH4, but it has the ability to reduce the acid to obviously the primary alcohol like this by using this LiLH4. And if you want to efficient reduction of this acid to alcohol, then we can use simply BH3THF, BH3. If you use the BH3 on the acid, so it will give the selectively this alcohol, and this reaction is quite good compared to the other reactions. Okay, we'll move to the question or problem here. So what we are up to, we were discussing how one can achieve this from this acetyl group to this here CH2. So for that, if you do the LiLH4 reduction, we can get the this our target molecule. So in which this entire carbonyl group is converted into the CH2. And also, I also like to take some more examples on such type of reduction reaction. And I think that you have already covered also, maybe by the videos covered by the professor. So if you want this compound, so how one can achieve this compound? Ignore about the other functional group. I will just quickly focus on the simple term, or I will just show the linear reaction. Forget about the retrosynthesis. So if we have this ketone, we can reduce this ketone to hydrogen by using the two different important two common condition SN in HCl, or we can also use the NaNH2, sorry, NH2 plus KOH. So these two are the different reaction condition. This is the Clemenson reduction, and this is the NH2 NH2. Basically, I think the Rosenman reduction. I don't know the name, but you should know the name for this reduction also. So in which we can convert this ketone to the this type of groups. So basically, we have converted ketone to alkane, right? So like this by using this type of reagent. So that you should know. Second slide, which I just like refreshed from the previous one. So which was this N. Now on adjacent to the this is R, this is R. So if you use the LiLH4, this can be, this is just, I will try the R3. Right. So this is one reaction in which you can see here. So you can see it was the carbonyl here, but now in the product, the carbonyl is just vanished. Right. So this also keep noted. The third reaction, uh, okay, the third one, I think this is also the good example. So if you have the ketone and you want this amine here, or so basically this ketone is converted into this amine. So for that, what you can do, you add the RNH2. So it will form the imine. So intermediate step was the imine formation, double bond N R, and followed by the reduction of this imine by using the NaBH3 CN. So it will give this amine, right? So you can also keep noted this reaction as well. So if you want to convert this ketone, so this ketone you can convert into the this type of amine by using first step was imine formation and second step was reduction of imine. So basically you have converted into the this type of, and you obviously know this ketone you can convert into the alcohol as well. So I don't think that's the just it's just like a toolkits for your retrosynthesis, right? So any doubt up to here? We'll move to the next questions. So here, this is the synthesis of this target molecule. So this is retrosynthesis already given. So we will just analyze how we do how here did the retrosynthesis. So here disconnection did. This is the synthon. This can be achieved from obviously the chloro or bromo substituted derivative from this one, and this is obviously another starting material. So from these two reagent, we can achieve the synthesis of this. So it's just straightforward synthesis. But how one can achieve this chloro at this position? This can be done by Cl2 plus acetic acid. So it will give the chlorination at alpha position of this ketone. So this is the reaction condition to do the chlorination here. And further addition of this nucleophile, it will replace this chloro, gives the our target molecule. And this is, you can see very simple small molecule. They can behave like a pretty good uh, pharmaceutical ingredient. So you can see here, this is like basically anti-parasitic drug, and it has the name nefimedone. Nefimedone. So that's the anti-parasitic drug molecule. Similarly, there are the next example that I have shown, and I think it is very similar as we have seen earlier some examples. So if you look at here, if you want to do the retrosynthesis of this molecule, how we can do? We can do the, as we've seen some examples, we can do this synthesis from this pH, from this imine, right? And it can be like this. This imine obviously achieved from this ketone plus plus this amine, six-membered ring, right? This NH. And further, if you do the retrosynthesis of this molecule, how one can do the retrosynthesis of this one? This is basically here. So that's the pH double bond O, positively charged. And here, this is the negatively charged ketone. Obviously, the base catalyzed reaction. So here, this O negative. And if you look at here, the linear synthesis for this molecule. So this is basically pH double bond O H. So like this can achieve from this small this. So if you look at the retrosynthesis, sorry, linear synthesis for this molecule, so these are the two starting materials, which is the benzaldehyde and this ketone, and also this is again one starting material. So if you want to do the linear synthesis for this molecule, how one can do? Just select the benzaldehyde. So that's the ketone. On addition of the base, this ketone forms this negatively charge at here, right? Enolate. So this enolate on reaction with this pH double bond OH benzaldehyde, it attacks on this carbonyl center. So it gives now H. This can be now OH and here pH. Upon oxidation of this one, what we can get? We can get this one again, pH. And further on reduction on reaction with this amine, it gives the formation of, and upon reduction of this imine, what we can get? We get our target molecule, pH. So this was our target molecule, right? Yeah, correct. So like this, we can do the linear synthesis. Any doubt in these steps? Okay, there is another one example. So which is very similar. I think we have already saw similar example, and the remaining part was the positive charge. So basically, this can be right. So this delta positive, delta negative. This is basically 1,3 addition reaction that sort of. So this is the retrosynthetic analysis for this molecule, right? So this is the one part. This is another part, and this was the synthon, and this is the synthetic equivalents. So this is one starting material. Another starting material is like this. So if you just want to do the linear synthesis for this molecule, so these two on reaction with the base, it forms the S negative attacks here. This will stabilize and further. So here SCH2 pH, this form negative, and this obviously abstract the proton from the solvent. We get our target molecule. So this is just a straightforward synthesis. So should we? I think this 1,3 addition type of examples that we haven't covered a lot. So I think we should cover that type of examples as well. So here, this is also one of the uh, useful architecture, molecular architecture for the synthesis of the some target molecules. So in which this position has the negatively charged, This position has the positive charge. Now one can do attack any nucleophile, any negative on this position, and we can increase this the chain length. So I think I should have some examples for similar. Mm, Not much examples, but I'll just take one example here. So let us say this is our target molecule, and how one can achieve the synthesis of this molecule. So if you look at this molecule, so this molecule can be cleaved here, and this molecule can achieve from such, this is negative charge. So I'll just break down this one. So this is now the positive charge. So from this type of systems, and obviously this can be from the this type of molecules, and this will be the butyl lithium negatively charged. That's the either n butyl lithium, or we can also Grignard C negative, EMG, PR positive. So like this. So this Grignard reagent plus this alpha beta unsaturated ketone can give the formation of this target molecule. So I hope this is much clear now. Now we have some additional some examples so that we can cover in the next video maybe. So before moving to the next, uh, does anyone have any doubt in the assignment? Okay, if you don't have any doubt, so we'll stop here for today, and maybe on the next Tuesday we'll cover some more problems. So in meantime, you can just take the photos of these some examples. So and practice. So more you practice, you can get uh, command over this retrosynthetic analysis. So these are some examples that I want to discuss today, but already it is 1 hour 15 minutes, so we can stop here for today. Maybe in the next video we'll discuss this. So these are some examples, just retrosynthesis, and these are I have taken from the Claydon. So I have already added the book Claydon on the OneDrive, so you can refer this detailed solution and the discussion for these some examples as well. Okay, we'll stop here for today and see you on next Tuesday.